Alright, so we're going to look at section 7.4, testing for proportions. And proportions are something that should help us get through looking at data in a larger context. I've been emphasizing since chapter 2, or at least I try to emphasize this idea that we want to look at our f over n. Right? And so we had frequency proportions when we were observing data where f over n gave us some percent. So we get this, f over n is equal to some percent. And one of the things I warned about was, let me see if I get, there we go, 0.009, I read that as 0.9%. These proportions that we did, correlate directly to some type of percentage. And so we would see this as a fraction, right? This could have been 9 out of 1,000 things. Or some fraction we did. We had the total amount in our sample, and we counted them up, and it turned it into a proportion. We verbally tend to say percent. We like the idea of percent verbally. And then later on, when we went into probability, we had theoretical probability, where if I draw 4, I have a chance of 4 types of cards out of 52. That's from the theory. I can count my outcomes, possible outcomes, and I can count my possible sample space, and I can get a probability out of it. We also said there was an empirical or a derived from observation probability. And if this was my population and I were to randomly grab in it, I have a 0.9% chance of grabbing whatever I observed here. And so we call these proportions. And so we can make hypothesi on proportions. And what's going to really come and help us out here is the binomial theorem. And so we're testing for hypothesi on proportions. I'm going to probably go right to examples on this to help us out here. So one of the things we want to remember is when we had a large number of n, we could have a binomial distribution. And in a binomial distribution, our outcome had 2 possibilities. True or false. You know, success or failure, we called it. Or failure. And giving those 2 outcomes, we could look at how many trials we had, and we could build the probability of getting so many successes based off the percentages. And we found that it was distributed similar to a normal curve. And so the more trials we run, the closer this comes to a normal curve. Well, normal curves and the tests we've been using correspond to z-tests. So any hypothesis testing that we want to do with proportions, we're going to want to use a z-test. And so it really doesn't set us too far away from where we've been. We get a hypothesis test. And in chapter 6 we did proportions on a confidence interval. Some things that we want to keep in mind, and I get very hand wavy on this, but the total number of things that we're looking at have to be times the proportion has to be greater than or equal to 5, and both of these conditions have to be true. The chance of success has to be greater than, or failure has to be greater than 5. And let's talk a little bit about success and failure, and then I'll look at this condition here. If I have a collection of things and I'm going to proportion it out, I've done a pie chart here, and let's see, I've measured loads of different things, and so we'll say this has 10%, this is 40%, this has 30%, and this is 20%. Whatever these things are, you know, thing A, thing B, thing C, thing D. We don't know what they are, but they have some percentage of our population. If I am only talking about the proportion of D, here, my probability of grabbing something in D is 20%, or my proportion is 0.2. My probability of grabbing something that isn't in D is the complement of that. It doesn't matter that there are multiple things here. I'm either in D or I'm not. I'm in D, not in D. And so that's what we're talking about, the proportions here. Now for these things to be greater than or equal to 5, you know, when n is really large, this, you don't really have to check this. Now, well, you do, but these numbers have to be really small. You're talking about 99%, right? For example, let's look at an extreme. If I had a 99% chance of success and a 1% chance of failure, whoops, 1, to get n times q to be greater than 5, greater than or equal to 5, I need 500n. But, I'm going to change colors for this here. In most cases, p and q are fairly close to each other. And when I say fairly close, let's talk about 70-30. And so to get the smaller number greater or equal to 5, well, I need n times 0.3 equals 5, or n equals 5 divided by 3, 0.3, which is what? 50 divided by 3, so 16 and change. So if these numbers are relatively close, our n doesn't need to be too big. Now the book's going to ask you to calculate it. If you ever ask me a problem on this, I'll tend to hand wave. I'll look at how big n is and how spread p and q are. If p and q is spread very, very far, I'll break out and calculate n. But if it's fairly close, if n is in double digits, we're starting to look good. But you should get used to double testing this, right? You haven't done as much mathematics as me, so hand waving isn't in your nature yet. But when you see more and more of these, you'll be able to start going, oh, well, I have enough. Well, if we do that, the thing we're going to use to get our Z score, the Z test, the statistic we're going to use is our sample proportion. And we're going to subtract that from the hypothesis claim of our population proportion, because the hypothesis is going to make some statement about P, and we're going to sample it. Now the binomial theorem told us exactly what the population standard deviation had to be if we were going binomial. So we don't need to know this. We don't have to worry about a t-test, knowing or not knowing. What we do is we pull from the binomial theorem the square root of pq over divided by n, or times n, and we throw it into our bottom here. And so what we end up with is, when we simplify everything, we multiply p and q divided by n. And this came from the binomial theorem of how we could estimate the standard deviation knowing p and q. And we work it all out. This is what we get for our Z test, which is nice. Now this p and q comes from the hypothesis. Our hypothesis is going to give us what we think the population proportion is from the claim, and then you get q given because q is always the complement of p, and you divide it by n. And so at this point we're into normal hypothesis testing realm. We have three possible hypothesized sets that we can do, some null, where we say the population proportion is equal to some proportion value, which gives us the alternative that it's not equal, which means this is a two-tailed test. And our alpha value is the sum or the percentage of the, that's going to be 1/2 alpha, and this is going to be the other half alpha. And so we are comparing against that. If we fall into there, we reject the null. And if we fall into the middle section, which I'll give a different color, right, we fail to reject the null in the middle section. And that's if we're making a claim that the proportion is exactly equal to a value. Well, we also had the hypothesis testing pair, where we could say this was greater than or equal to some value, which gave us an alternative where the proportion would be less than some value. We get this pair. That, because the alternative points left, becomes a left-tailed test. And our significance level value is the probability of landing in that rejection region, where we reject the null. And if we fall out of the rejection region, we fail to reject the null. And then there's one more where we switch the greater than and equal sign. Let's scroll up a bit. And this is a right-tailed test, with alpha defining that rejection region, and in there we reject the null. If our test value, if the z value of our test value falls in there, we reject the null. And if the test value or our z-score falls within here, we fail to reject the null. Come back up here. This is the z test we're going to use to get a z value, and then we can compare the z value to the critical values, or I think your book uses z naught for them to separate them from confidence critical values. This dividing line is the comparison that we use, and if you're in the region or not determines if you accept the null or not. All right, so and we can also, from the z value, so you can use z and compare to alpha's z critical value, or you can use the z-score to create a p-value and compare to alpha. They do the same thing. So what I'm going to do is I'm going to now use this equation. I'm going to scroll up here and show it, to do some hypothesis tests on some proportions. So we'll do a couple examples. The testing mechanism is the same. The question we're asking is different because we're asking on proportions. So I'll upload some of those examples.